everyone. Today we're diving into numerical summaries from sections 3.1 and 3.2. We'll pin down how to describe a data set using measures of center and spread, and then we'll finish with the empirical rule. So let's get into it. This is some good stuff. So when we analyze a distribution, we always look at three things. The first is shape, the second is center, and then of course the third is spread. So shape gives us the pattern of the data, which is really important. Center tells us what's typical, so what kind of what it sounds like, what the middle is, what the average is. And then spread shows us how much variability there is, and there's always going to be variability amongst different sets of data. So we're going to keep these three things in mind. They work together to tell us the story of the data. To find the center of our data, we use measures of central tendency, and here they are. Here's the three of them. We've got the mean, the median, and the mode. So the mean is the average. Hopefully you've worked with averages before. The median is literally the middle data point, and then the mode is the data point that shows up most frequently. Here's a quick tip. If you ever forget, think of them alphabetically: mean, median, mode, average, middle, most, right? So mean comes first, that's the average. Median is the middle, and mode is the most. A quick reminder, because statistics is a science, we always start by clearly defining the purpose and scope of our study, because that choice affects which formulas and symbols we use. So whichever one of these we wind up using, we're going to kind of calculate in a different way, and we have different implications with each one that we're going to talk about as we go on. Okay, so here's our first example with high temperatures in May. Okay, we've got them listed. So high temperatures for the first week in May are recorded as 66 degrees, 68 degrees, 67 degrees, 57 degrees, 54 degrees, 57 degrees, and 51 degrees. Now, first things first, if our study is only about the first week in May, that's really the only thing we care about, then our data set here is the population, because we have all of it. We have every single data point from that first week in May, every single high temperature, right? But if our study is about the entire month of May, then this same data set becomes a sample, because we only have part of the data, right? There's about 4 weeks in May. We've only got one of them. So it's really important to define the scope of our study, right? Which is kind of what we talked about on the last slide. So the exact same numbers can be a population in one study and a sample in another. The role really just depends on our research question. So depending on the scope of the study, we will have to use different symbols to denote measures like mean, even though we may use the exact same formula to find it. So first of all, we use the Greek letter mu to stand for our population mean, okay? And then if we're talking about a sample, not a population, then we use Roman X bar. So we use Greek letters when we're talking about populations and Roman letters when we're talking about samples, okay? Capital letter N, that just means the size of our population, whereas lowercase n would mean the size of our sample, okay? And then this symbol right here is called sigma. It's the Greek letter sigma. It means summation, which basically is just a shorthand, a long-winded fancy word for saying add everything up, right? If we sum everything, we're adding it up, okay? So these symbols kind of help readers instantly see whether we're talking about a parameter for a population or a statistic for a sample. Oh, and there's one more. X sub I right here, that means some generic data point. So, you know, if we're thinking about those high temperatures in May, maybe 1 point would be 57 degrees. So in this study, it's about that first week in May, right? Which means we have a population and we want to know the average or mean temperature. So we're going to use this formula right here, okay? Remember that Greek letter mu means mean, population mean. And then we have all those other symbols that we just talked about. So we've got the summation of x sub I. That means we're going to add up. Summation means add up. Xi means all the data points, right? So we're going to add up all the data points and divide by the number of data points. That's what this capital N means, however many data points were in our population. So you guys have probably computed averages before, right? You take all of the numbers, add them up, and divide by however many numbers there are. That's just how we compute an average. This is just a fancy formula for it. And we're making sure that we designate that we're looking for the population mean, which is why we used mu and capital N here. Okay, because it describes a population. So when we do that, right, when we plug all of our high temperatures from the first week of May in, add them up, there were 7 different temperatures, right, 7 days in a week, divide by 7, our average temperature was 60 degrees. So the mean temperature for the first week of May was 60 degrees, and because this describes a population, this is a parameter, right? We were only concerned with the first week of May, that was our entire population, so this this population mean, 60 degrees, is a parameter, not a statistic, because it's describing a population and not a sample. Now, if we change the scope of our study a bit, and we're talking about the entire month of May, that means that that very first week was just a sample, and we want to know the average mean temperature. We're going to use this formula right here. Notice that mu, that population mean, has changed to x bar, right? Our Roman x bar here. And it looks pretty similar, except those, just some of those symbols have changed. We have x bar instead of mu. We have a lowercase n instead of uppercase n, meaning we're dealing with samples. So when we see x bar and lowercase n, we're now talking about a sample mean, okay? So now we're still going to add up all those data points and divide by the number of them. So we're still adding up the same numbers, dividing by the same thing. And we get the same answer, but only now that 60 degrees is no longer a parameter because it's not representing a population mean. That 60 degrees is a statistic because it's now representative of a sample from the population of the entire month, right? So this is just one sample from it. Okay, so we want to be really explicit and careful when it comes to understanding whether we're dealing with a population or whether we're dealing with a sample. So the working definition of statistics, it's the science and art of collecting and organizing, summarizing, and analyzing information when some information is missing. Often when we can't get everything, we use statistics to help us out. So the median is the middle of a data set arranged in order, okay? We use this capital M for median. There's no distinction for population or sample. No matter what, when we look for the median, we just use this capital M. If there are an even number of values, what's going to happen is we're going to line them up in order, and there's not going to be a middle point. So what we wind up doing is we average the 2 middle points, and you'll see that in a minute. We're going to do an example of that. So let's take a look at what this looks like. So let's find the median temperature for the first week of May. Now this is the data set that we started with. It was unordered, meaning it doesn't go from smallest to largest, okay? So if we want to find the median, the first thing we want to do is we want to line it up in order. So now notice we're starting with the smallest value, and then the next, and then we move up to the next smallest and the next smallest, and on until we have them lined up from smallest to largest. Okay, and then we're going to find the one exactly in the middle, and as you can see, that's 57 degrees. Okay, so that means the middle of the data is 57 degrees, so the median is 57 degrees. And you know, just a quick tip, for order first, then look for the middle. Don't kind of try and eyeball the middle from an unordered list. It might look really obvious, but oftentimes we're going to get that wrong. So make sure you're lining them up first. So now let's talk about that last measure of central tendency, the mode. And it's exactly what it sounds like, right? Mode kind of sounds like most. It's the data value that appears the most frequently. So if every data value appears the same number of times, we actually say there is no mode, right? If 2 different data values appear the most, like if we had 57 degrees, 57 degrees, 49 degrees, 48 degrees, 51 degrees, 51 degrees, so we have 57 degrees and 51 degrees appearing twice, then we call that bimodal. And if 3 or more different data values appear the most, the data is multimodal, all right? And what's kind of cool about this is that the mode is the only measure of central tendency that we can use to describe qualitative data, all right? Like the most common eye color or something that's not necessarily based in numbers. So going back to that same data set that we've been looking at, if we want to find the mode temperature for the first week in May, we're going to look at our data here, and we're going to find we're going to list the data and tally the frequencies. Okay, so if we do that, we can see that the mode of our data is 57 degrees. It's the only data point that shows up twice here, right? Every other temperature shows up only once. And so since 57 degrees shows up the most often, it is our mode. So now let's talk about something really important. When data are skewed, okay, here we've got skewed left, here we've got skewed right, and here we've got a pretty symmetric data shape of data here, right? You can see this one has a longer tail on the left, this one has a longer tail on the right, but here if we were to just draw a line right down the middle, that's called symmetric data. So when data are skewed either to the left or the right, the extreme values in the tail pull the mean, right, that average value, toward the tail. Okay, so if we've got a data point way out here, it's going to pull that mean towards it. So the median barely budges. So we can call the median resistant, okay? So what you want to understand is that when we have skewed data, it's better to use the median than it is to use the mean as our measure of central tendency, because when we have skewed data, that means we have some data points that are going to pull that mean down, whereas the median just kind of sits in the middle. It's a much better reflection of what the middle is. So the median is not affected by those extreme values. It is resistant to them. And so that's an important thing to keep in mind when we're trying to consider, do we want to use the mean, the median, or the mode? So now let's discuss measures of spread, which is another hugely important factor in the study of statistics. We're going to just start with some very basic definitions here. So when we say dispersion, that's the degree to which data is spread out, okay? The range is the difference between the largest and smallest data values in our data set. So we denote range with capital R. We can calculate that by taking the max, our largest data value, and subtracting the smallest data value from it, the min, and that will give us the range of our data. Deviation is a measure of how far away a data point is from the center, and we can calculate, and then deviation about the mean is the difference of a single data point from the mean. So remember that x sub I stands for any data point, mu stands for our population mean. We can figure out how far away that single data point is from the mean if we subtract the two, because subtraction is just another way to calculate distance, basically. And then we have standard deviation, which is a measure of the deviation from the mean for all data points in a set. It's kind of like the average distance any point might be from the mean is a way to think about that. And we're going to use standard deviation a lot. Okay, so now let's practice calculating some of those measures of dispersion that we just talked about. Let's find the range of temperatures for the first week in May. So remember, range is just the max minus the min. So here our biggest, highest temperature was 68 degrees. That was our max. Our lowest temperature was 51 degrees. That was our min. So we subtract max minus min, and we get 17 degrees. So the range of temperatures for the first week of May was 17 degrees. So now let's find the standard deviation for the first week of temperatures in May, okay? First thing we're going to do is list each day's temperature and compute its deviation from the mean. And again, whether it's a population or a, or a sample, we already know that the mean, or x bar, we computed that earlier, was 60 degrees. So I have all my temperatures listed here, right? All my x sub i's are listed here in the left side, all my data points for the first week in May, right? We have listed. And so if we subtract x sub I minus mu, each of our data points minus the population mean, right? Here it would be 66 minus 60, we get 6 degrees. 68 minus 60, we get 8, and so on and so forth. And notice some of these are positive and some of these are negative, okay? If it's positive, all that means is that our data point was above the mean. If we get a negative value, that means that our data point was lower than the mean, okay? So notice that when we add all of these deviations about the mean, they add to 0. And that's because the mean is the balance point, right? All of these positives sort of cancel out the negatives. That just sort of makes sense. Think of it like the balance point of like a playground seesaw. The ups and downs kind of cancel out, which is why the deviations always add up to 0. So notice while the deviation from the mean is useful for individual data points, it's not really useful for measuring the spread of the entire data set because the sum of all those deviations give us 0. And that's because the mean is the center of our data set, right? So they just cancel each other out. So let's keep going with this, right? We're not going to really use deviation because it doesn't really help us much, which is why we want to use something called standard deviation. And we're going to keep going with that idea. So to measure the spread without that canceling problem, right? Without them canceling each other out when we sum them all up, we need to make all those deviations positive. And so what we wind up doing is we wind up squaring them, and that gets rid of those negative signs, right? So we have 6 squared is 36, 8 squared is 64, 7 squared is 49, negative 3 squared is positive 9. So it takes care of getting rid of all those negatives. And so part of calculating the standard deviation is not just finding the differences. We then need to square them. And then there's actually one more step. We'll take the square root to get the standard deviation. So let's keep going. So what we're going to do next is we're going to find the average of the squared deviations. And that actually has its own name. It's called the variance. And because this is a population, we're going to call it our population variance. So far what we've done, right, on the previous few slides is we took each data point, we subtracted the population mean. Okay, some of those values were positive, some were negative. When we added those all up, we got 0, so we said no. Instead of adding those up, we're going to square them first, and then we're going to add them all up. And so when we wound up squaring all of those deviations about the mean and adding them up, we get 284. And then we want the average of those, right? So to find an average, we add everything up and then we divide by the total number of data points. Here we had 7, right? There's 7 days in a week. So we had 7 different temperatures. When we divide by 7, we get 40.571, okay? However, we did have to square the difference to make it positive, right? We had to square all of those deviations in order to kind of solve that canceling problem. So we had to square everything to make it positive. So this is actually, this number right here, this value, now puts our units in degrees squared. This is 40.571 degrees squared, and that's really not very useful. So we need to take the square root in order, that's kind of the last step here, in order to give us the final standard deviation. And so when we find the standard deviation, we have to take the square root of our variance here. So the square root of 40.571 is about 6.37 degrees, meaning the standard deviation for the high temperature for the first week in May is 6.37 degrees. So if we have our population mean at 60 degrees, right, that's the middle, okay, kind of the middle there. That means each data point is about 6.37 degrees away from that mean. That's what the standard deviation is telling us about how far away the data points, how spread out they are. And that's why it's a really important, useful measure of spread. So remember, when we're talking about this stuff, notation really does matter. When we're talking about the population standard deviation, which we were computing for our example about the temperatures in May, we're going to use the Greek lowercase letter sigma right here. So this is our population standard deviation. And then, of course, sigma squared is our population variance, right? We know that. However, when we're talking about a sample, we don't call it sigma anymore. We notate the standard deviation S for sample standard deviation, okay? And then, of course, our sample variance would be S squared. So this helps our reader know instantly whether we're talking about a sample or a population just by looking at the notation. Because if we see sigma, we know it's population standard deviation. If we see S, we know it's a sample standard deviation, and it's a statistic. So here we have, so these sigma and sigma squared are considered parameters, whereas S and S squared are considered statistics. Okay, so when we're dealing with samples, right, when we calculate the sample variance, we actually wind up dividing by n minus 1 instead of n, like we do for the population variance. And that's because we need to make that sample variance a little bit bigger than the population variance, because with a sample, we're missing information. Remember, a sample does not represent the entire population. It's a small subselection of it. And when we're missing information, that means that we need to correct for that. And typically, if we had all of the information, the entire population, it would actually be more spread out than the smaller sample that we have. And so when we take the sample variance, we kind of have to correct for that by dividing by the n-1. And we call n-1 our degrees of freedom. And so really at the end of the day, we do this because we need to remove bias, right? Bias is when a statistic representative of a sample differs from the true parameter that represents the population, okay? So think of this n-1, this degree of freedom, kind of like a little safety net, since our sample doesn't actually capture all of the variation of the population, right? Think of how variable a population can be. Dividing by the one less keeps our estimate from being too small. So it kind of removes that bias from it. So now suppose we want the standard deviation for the entire month of May. Okay, now that means that that first week in May is no longer the population because we don't know every single high temperature for the entire month of May. We only know for 1 week. So now it becomes a sample. Okay, we have the same data set. So the first steps are the same until we calculate that variance. So we're still going to compute the deviations, square and average them. But now, right, we're still computing these deviations right here, squaring them, adding them up. But now instead of dividing by 7, right, it's no longer a population, so we have to divide by those degrees of freedom. We need to kind of make up for that bias of this being a sample now. Okay, so instead of dividing by 7, we're going to divide by 7 minus 1, which is 6. And when we do that, notice we get 47.33, which is slightly higher, right, than what we computed when we computed this as a population. And so our sample standard deviation will be the square root of the sample variance, which gives us 6.88 degrees. So the standard deviation, the sample standard deviation for high temperatures in May is now 6.88 degrees. Again, a little bit higher than what we calculated when we got the population. So as a rule of thumb, in general, the more spread out the data, the greater their standard deviation is, okay? If the standard deviation is 0, then there is no deviation, which only happens when, if you think about that for a second, all the observations are the same, right? If there's no spread, they're all right here. They're all right at the center. There's no deviation there. But if they're more spread out, that standard deviation is going to be bigger and bigger because standard deviation measures the average distance any single data point is from the mean. Okay, so the more spread, the greater the standard deviation, the greater the distances. So for example, if your data set was 20, 20, 20, 20, 20, 20, 20, then the standard deviation is 0. There's literally no spread from the mean, okay? Now, in practice, you are almost never going to be calculating a standard deviation by hand. You should always use technology to complete complicated calculations. But it's really important to make sure you understand what you're calculating and the notation, because it's going to kind of give you this foundational theoretical idea of what you're actually doing. I could give you a formula for standard deviation, or you could just plug it into a computer, but if you don't actually understand where that formula comes from and why we use it, you don't actually understand what standard deviation is, right? But once you start to kind of think about where that formula evolved from, you understand that standard deviation is actually measuring the average distance from the mean, okay? And so that's why it's really important to kind of just understand how we build that formula and why it actually, how it works and why it actually measures what it's measuring. So your TI 8384 calculator makes the distinction between population and sample when calculating one variable statistics. Okay, so and in Excel you need to make the distinction when using formulas to ensure you get the correct answer. So in your calculator, it's going to, and you'll see that in the homework, the technology help resources provided in this module. But just make sure that when you're using Excel, you understand that you kind of have to make that distinction when you're using formulas rather than calculating by hand to get the correct answer using stdev.p for population or stdev.s for sample, okay? So always pick the function that matches your study scope. Make sure you know whether or not you're dealing with a population or a sample, okay? That's important. Okay, last big thing we're going to talk about in this video, which is super important. the empirical rule. So the special case, when the data is bell-shaped, okay, we're talking a lot about that in this class, meaning that the data is unimodal and symmetric around the mean, median, or mode, we can use the empirical rule, which is really helpful. And so that says that approximately 68% of the data lie within one standard deviation of the mean. So that means that approximately 68% of the data lie between mu minus one standard deviation or mu plus one standard deviation. So one in either direction, to the right or to the left. 68% of the data will fall there. And approximately 95% of the data will lie within two standard deviations of the mean. Okay, so same kind of deal here. If we go out 2 standard deviations to the right or 2 standard deviations to the left, that's going to be 95% of our data is going to fall in there, of our data points. Anything sort of outside of that is going to be called unusual, okay, these outlier data points, if it's not within those 2 standard deviations. And then approximately 99.7% of the data, almost all of it, will lie within 3 standard deviations, okay? So if we go out 3 standard deviations to the right and 3 standard deviations to the left, we will have almost 100% of our data, which is pretty cool. So I don't know about you, but I do a lot better with visuals. This is a visual of the empirical rule just to kind of help you lock it in. We've got this nice bell-shaped data. Here's our mean right in the middle. And so if we go out 1 standard deviation in either direction, we've got 68% of our data, right? 34% of it should fall here and 34% of it here. If we go out 2 standard deviations, now we've got 95% of our data falling within those first 2 standard deviations. And then if we go out 3, we've got 99.7% of our data. And remember, anything outside these 2 standard deviations, right, it's kind of considered unusual, all right? So this is kind of like, keep this visual in your brain as you work through to kind of give you an idea of whether your data, where your data points are lying, how far away from the mean they are, and whether they're unusual or not. And just to kind of give you a context and an application of all that, so the average height for adult men in the United States is normally distributed with a mean of 70 inches and a standard deviation of 3 inches, okay? So the mean, the average height for a man is 70 inches. And if there's a standard deviation of 3 inches, that means that most men, about 68%, have a height within 3 inches or 1 standard deviation of the mean. So 3 inches to the right would be 73 inches, 3 inches to the left would be 67 inches. So most men, about 68% of men in the US, are going to be somewhere between 67 and 73 inches tall. Almost all men, about 95% of them, have a height within 6 inches, right? 2 standard deviations of the mean. So if we go out 3 more inches from that first standard deviation in both directions, that means 95% of men are going to be between 64 and 76 inches. And then approximately 99.7% of men are going to have a height within 9 inches of that mean. So 99, almost 100% of men are going to be between 61 and 79 inches. So we're going to talk more about these things in the next video, but this should hopefully give you enough to kind of go off and start the first 2 sections of chapter 3, and we're just going to carry these ideas through into the next few sections. So good luck. Let me know if you have any questions, and thanks for being here.